To talk about NoStar, which is a library of verified high-performance secret channel protocol implementations. NoStar is a new addition to the Everest project, whose goal is to develop a library of verified components for the HTTPS ecosystem. The reason behind Everest is that when dealing with such components, it's possible to do a lot of mistakes which can have very dire consequences. For example, when you deal with cryptographic primitives or message passing and formatting, you can very easily do memory and type safety errors, and so have buffer overflows or dangling pointers. Moreover, all those components must be highly optimized, and when performing those optimizations, we can do a lot of errors. When you continue to move up the stack, for example, when studying protocols, you want to ensure that you have some security properties. For example, that when you send some secret data to someone, this data remains secret, or that when you receive a message, this message was sent by Alice and not by, for example, Eve. And when you continue to move further up, you have to deal with long-term key storage and validation, session management, etc. So, in the Everest project, we decided to apply formal methods to verify those components. Applying formal methods means to formally specify how those components should behave and prove in some way that they satisfy those properties. One big issue here is that we have to deal with a lot of protocols which are used in a lot of very different situations. For example, we have TLS, QUIC, or Signal. And verifying every one of those protocols requires a huge amount of work. So the big question is there a way of factorizing this work? And the answer is actually yes, and it is the reason behind the NoStar project. The NoStar project consists in developing a compiler for the noise family of protocols. The noise family of protocols consists in 59 protocols which are used in real-world applications like WhatsApp, WireGuard, Signal, or Facebook Messenger. Moreover, we decided not to stick at the level of protocols and go further up by developing verified high-level libraries on top of them. Before going further into the details of NoStar, it is important to understand a bit what noise is made of. One important thing is that noise introduces a very succinct and easy to understand notation to describe handshake patterns. So we call those patterns. A handshake is basically used to set up a connection between different parties in order to later on exchange messages. For example, here we've got 3 different patterns for 3 different protocols, and they are extremely different and have extremely different properties and usages. Those protocols are made of pre-messages, which are messages which must be exchanged before the handshake begins and allow to exchange keys by using, for example, public key infrastructures. They are made of handshake messages, which allow you to generate and exchange more keys and perform Diffie-Hellmans to compute new symmetric keys from those exchange keys. And finally, from a transport phase during which we can exchange an arbitrary number of messages. In the case of the first pattern on the left, which is called X, every pattern has a name, the initiator must know the responder's public static key beforehand because of the per-message. And then during the handshake, the initiator must send his own public static key to the responder. The initiator is always on the left and the responder on the right. And finally, during the transport phase, the messages can only go from the initiator to the responder. The handshake is only one way. This protocol can be seen as a substitution for existing protocols like Knucklebox or HPKE. With NX, on the contrary, only the responder is authenticated, but the transport messages can be sent both ways. A typical use case is a client connecting to an authenticated server. Finally, in the case of IKPSK2, both parties are authenticated, like in X. And if you do a detailed security analysis, you can see that from the very first message, the encrypted payload has very good security properties. However, you need 3 messages to fully complete the handshake. This last pattern is actually very interesting and is used in WireGuard, and a variant of it called iKey is used in WhatsApp. As I've said, Noise allows today to define 59 protocols, and actually more if you take into account piped protocols. And this number might increase if more features like signatures are added. So we decided to implement a verified compiler for those Noise protocols. This compiler is made of several parts, the first one being what we call a formal specification. A formal specification consists in a very simple implementation, which is designed to be as succinct and clean and easy to read as possible. The idea is that you have to be able to easily convince yourself that this implementation is correct. Then we write a lower level implementation which deals very precisely with a lot of features like buffers. And by using what we call a theorem prover, in this case F star, we prove that this low-level implementation indeed behaves the same way as the formal specification. This proof is made in several layers. At the very bottom, we reuse the cryptographic primitives from the Hackelstar library, which is one component of the Everest project. And then, above this, we implement the protocol layer by carefully reading and implementing what is written in the official Noise technical paper. Of course, as I've said, we don't stop there because protocol functions are actually quite low level, and it's possible to mess things up when you use those functions. So we add more layers to deal with high level features like key storage and validation, peer management, state machine, sessions, etc. Once all this is implemented and verified, it is possible to take the low-level code and compile it to high-performance C code specialized for every pattern, X and X, IKPSK2, etc. As I've previously mentioned, the security properties vary with the different patterns. So we decided to model that by using a framework called Delignat-Lavaud, which uses what we call a symbolic model of cryptography, and to prove various properties about those different layers. Those properties are expressed by using formulae which are easy to understand and allow to say who can know a message at a given moment, or to be more precise, which keys need to be compromised in order to compromise a message, and they are precise enough to model properties like forward secrecy. The generated C code looks like this. So here are a few signatures which come from IKPSK2. There are a lot more of them to provide users with a full library for noise. But those are already very significant. Those functions were designed to be as easy to use, user-friendly, and idiot-proof as possible. And you can see here some snippets of code from the implementations themselves. Finally, we benchmarked our code and compiled it to existing implementations of Noise. And thanks to the very good performance of the Hackelstar library, our code is competitive against all those implementations and actually beats them all at the exception of WireGuard, which is specialized for IKPSK2. As a conclusion, I've introduced NoiseStar, which is a new component of the Everest project and consists in a compiler for the Noise family of protocols written in F star and verified once and for all. This compiler generates a high-performance verified library stack and is complemented by protocol and API security proofs. Thanks for your attention.